All right, welcome back. Our next speaker is Seth Koren from University of Notre Dame, who's going to tell us non-invertible symmetries and model building. Take it away.
Hey everyone, and thank you to the organizers for having me. I am a particle physicist, and I would like to tell you one way in which generalized symmetries have been telling us, giving us more information into theories of particle physics. As you can see from the references, I've been spending some time these years thinking deeply about symmetries in theories of particle physics, as one should. I'd like to tell you in particular about this work with my fantastic collaborators Clay Cordova, Song Hong, and Kantaro Omori, mainly. Before I get to that, there's some background for me to cover. I'd like to remind you what particle physics is, and also how particle physicists use symmetries to think about physics. Okay, so starting with, let me take you through the fantastically successful standard model. Of course, this is the theory that incredibly accurately describes you and everything you interact with on a daily basis, down to distances of something like 10 to the minus 19 meters. This is amazing, and it does so with only a couple dozen free parameters. I'll take you through it briefly. The parts that we need, again, I'll bring up a bit later. So the standard model is a Yang-Mills theory. We really only know the Lie algebra, SU3 cross SU2 cross U1. We have a single scalar Higgs boson that condenses and spontaneously breaks the electroweak part of the gauge group down to electromagnetism. And we have chiral matter with 3 generations of these Weyl fermions that only get their masses through their Yukawa couplings to the Higgs bosons. I've color-coded the quarks in green and the leptons in purple, both left and right of each. I've included the right-handed neutrino. You'll notice, although we don't strictly know that that's how neutrinos get mass, but this will come up later in my talk. And again, let me say, this is an amazing achievement of humanity to write down this microphysical theory of the universe. But we are not to rest on our laurels. We know there is more to uncover. We have very, empirical needs for things like dark matter and baryogenesis in the early universe, but also just generally as reductionists, we would like to have an even simpler UV theory that explains to us why we live at this particular place in the standard model parameter space. So how are we to go about thinking about what that should be? Well, of course, we've long understood that symmetries offer us crucial guidance here, and this is this principle of naturalness. Now, you may have heard people say some awfully silly things about naturalness, so please forget them. Naturalness, at its core, is the simple statement that if I give you a UV theory and you coarse grain down into the infrared, you will generate all operators that are allowed by global symmetry. And generically, with coefficients of order 1 in the natural scale, the UV cutoff of the theory. Okay, now what does that look like in some particle physics example? Well, let's go to the far infrared of the universe in QED. There, the proton is a vector-like fermion. And we can ask, why is the mass of the proton so far below some UV scale, maybe the Planck scale? Well, this principle of naturalness would tell us that the proton mass should be order 1 in units of the UV cutoff. And indeed, as you know, the proton is actually a composite fermion with a mass around the dynamical scale of QCD. Great. And furthermore, once we go to the UV theory of QCD, we learn from asymptotic freedom that you can ask, why is the QCD scale so small? Well, asymptotic freedom tells us that this theory can dynamically generate this small scale. So this example illustrates this general expectation that either a parameter is naturally of order 1, or there's some sort of non-trivial mechanism that explains why it's so small. But now, someone may object, what am I doing talking about the mass of the proton? The electron is much, much less massive. Is it a big problem that we didn't find the electron was composite? Well, for that we need a subtler understanding, not just of when symmetries are good, but what about broken symmetries? And this is something that Tuft taught us many years later. Tuff tells us that if we have a zero-form global symmetry that is broken solely by one parameter, then that parameter automatically can remain small. If you set it small by some mechanism in the UV, it automatically remains small into the infrared. And so how does that come to bear here? Well, when we embed QED into the standard model, as I said before, we learn that the electron is chiral and one of three charged leptons that get their mass from the Yukawa coupling to the Higgs boson. And the question of its mass now factorizes into two different things. One is, why is the electroweak scale so far below some UV scale? This is very hard. It's called the electroweak hierarchy problem. You can ask me later. But the other question is, we observe some crazy hierarchical Yukawas. Particularly in the lepton sector, the eigenvalues are very hierarchical. And why that sort of structure? And we are comforted by the fact that the standard model Yukawas are in fact technically natural, because they are the only place in the standard model that the three generations are distinguished. They have all the same gauge couplings. And we can systematically understand this by what's called spurion analysis. This is all very easy stuff. When you take the Yukawas to zero, when you turn them off, then each type of fermion has classically a U3 global symmetry, rotating the three into each other. When we put the Yukawas back in, we can assign the Yukawa a spurious charge under these flavor symmetries to formally restore the flavor symmetries. And now, when we go and calculate anything we want, the quantum field theory doesn't know that those are actually numbers and not background fields with this representation. So everything we calculate has to respect this spurious symmetry. And in particular, the renormalization, that means the renormalization group evolution of the Yukawa matrix must be proportional to itself, since there's nothing else you can write on the right-hand side with the right spurious symmetry charge. Okay? And so that, that comforts us, that tells us that, well, okay, it's fine that we haven't uncovered yet the mechanism for flavor in the standard model. That can happen at some UV scale, because of this fact that the standard model Yukawas are technically natural. If there's some as yet unknown mechanism that sets up this crazy hierarchical structure for the Yukawas in the UV, at least that is stable upon renormalization group running into the infrared. So this is great. That helps us sleep at night as standard model physicists. But understanding that something is technically natural doesn't offer us any insight as to what the mechanism might be, why they might be small in the first place. Okay? And that is the place where we've learned concretely more by understanding generalized symmetries. Let me remind you of this setup we've already seen a couple times, and you're all familiar with, of four-dimensional non-invertible chiral symmetries. We have a Yang-Mills theory that has a one-form magnetic symmetry, and our theory has a chiral symmetry, which has an anomaly. And so, as we've said, before you might have naively thought that the symmetry should just be broken, but in fact we can recognize on the right-hand side that that is made out of currents. And so we can write down, in fact, this non-invertible symmetry defect operator that talks to both of these currents. And in particular, now it acts both on the local fields and on the Tuff lines. None of the technical details are going to matter here. Just schematically, they act on the Tuff lines roughly by putting them into dions, giving them a small dionic charge. But the point is, now that we have the symmetry defect operator that acts both on local operators and on the Tuff lines, that this symmetry must break when we go to the UV and we see dynamical magnetic monopoles in our theory. But, if this non-invertible symmetry was the only symmetry protecting some local operator, then when we go to the UV and see it's broken by dynamical magnetic monopoles, that operator now must be generated. And so this gives us sort of a refinement of this spurion analysis. If we, in our infrared theory, find that we have a parameter that breaks a non-invertible symmetry of the infrared theory, then we learn that that operator, that parameter, could be generated by non-perturbative gauge theory effects in some UV theory that introduces the correct magnetic monopoles. And this is a strategy we're going to use to make some, get some insight in some examples. If this isn't entirely clear, hopefully it will become so in the next slides with the examples. So how are we going to use this? We're going to go beyond the standard model by gauging some approximate U1 global symmetries, zero-form global symmetries. I'll remind you again, the standard model is a chiral gauge theory that has 3 generations of these fermions. The quarks in green have this U1 classically conserved quantum number that for historical reasons is called baryon number. The leptons, more sensibly, carry lepton number, left and right-handed. Now, thinking about gauging some of the approximate global symmetries of the standard model is nothing weird. I'll remind you parenthetically that the reason that some grand unified theory works, SO10 or something, is because the standard model, one generation of the standard model, has an approximate SO10 global symmetry already that you upgrade to a gauge symmetry in that grand unified theory. Here I'm going to be less ambitious. We're just going to think about gauging a U1 symmetry. But we can't do it arbitrarily because the standard model is a gauge theory already. We have to be aware of some triangle anomalies, and we can't upgrade anything anomalous, of course, to a gauge symmetry. One way to find an anomaly-free symmetry to upgrade to a gauge symmetry is to do baryon minus lepton number, as you probably have heard. But alternatively, we can exploit the generation structure of the standard model. And the fact that I can think about gauging, for example, lepton number of the 2nd generation minus lepton number of the 3rd generation. And then if lepton number of the 2nd generation had whatever mixed anomaly that would be dangerous, that cancels against lepton, when you include also minus lepton number of the 3rd generation. Okay? So indeed, this is the strategy we're going to pursue, starting with, in fact, L mu minus L tau. L mu minus L tau has lots of phenomenological motivation. It's been studied tons and tons of times for neutrino masses, G minus 2 of the muon, B anomalies, yada, yada, yada. So we're going to gauge the zero form U1 L mu minus L tau. As you know, that we then get a U1 magnetic one-form symmetry. And any mixed Tuft anomalies that L mu minus L tau had are now upgraded into ABJ anomalies, and in particular, there's a U1 that I'll call U1X, the exact identity won't matter, that has exactly this sort of ABJ anomaly, where we can again recognize the magnetic one-form current on the right-hand side. And so, this U1 in L mu minus L tau has been turned into a non-invertible symmetry. And in fact, the business end of it is a certain generation-independent Z3 subgroup, which acts like this on the local fields. It acts like lepton number on the standard model leptons and gives right-handed neutrinos the opposite charge. And neutrino masses all break this non-invertible symmetry. So let me remind you why that's interesting is because there's this important standard model naturalness issue, which is, as the standard model was originally formulated, neutrinos were exactly massless. Now, decades later, we know, in fact, they are massive, but they have very, very tiny masses. Comparing the heaviest charged lepton to the heaviest neutral lepton, in fact, the hierarchy is about 10 to the 11, a crazy splitting then. So why in the world could this be? Well, we just found that in this L mu minus L tau theory, neutrino masses break a non-invertible symmetry, which is this setup I was exploring earlier in general. So we could try to find a UV theory that breaks this non-invertible symmetry with, by introducing the correct magnetic monopoles and generate the neutrinos by non-perturbative effects.
Great.
Yes?
So you're gauging this U1 symmetry, but shouldn't you also add some Higgs that makes this additional photon massive?
Yes.
Okay.
Yeah, we don't see another photon in the infrared. This is the normal strategy, just like we don't see the SO10 gauge photons. Of course. Good. So, indeed, the non-invertible symmetry analysis I went through in general tells us that we should look for now a UV theory that embeds L mu minus L tau and breaks the magnetic one-form symmetry explicitly by including the appropriate magnetic monopoles. And once you know what you're looking for, it's not so hard to find the nice thing to do. You still have to be a good particle physicist and model builder and quantum field theorist. But in fact, the very nice thing to do, it turns out, is to unify the three families of leptons into a non-abelian gauge theory of lepton flavor, and just put each of the leptons into the fundamental, or anti-fundamental, of course, of SU3. And that does introduce Topf-Polyakov monopoles for LV minus L tau. So then, what is the benefit? What happens in this UV theory? In the UV theory, we can write down, at some UV scale, only the charged lepton Yukawa. I put the tau Yukawa because that's the largest, but it's flavor symmetric because we have a gauge flavor. Without writing down the neutrino Yukawa, there's a classical symmetry protecting it. And as we coarse grain now, RG evolved down from the UV toward the infrared, and SU3 is spontaneously broken, we find Topf vertices that are generated, instantons generate the Topf vertices, which are interactions among the charged fermions, which together with the charged lepton Yukawa here, in fact, generate for us a Dirac neutrino Yukawa, which is indeed exponentially suppressed from the charged lepton Yukawa by an instanton action. Okay? And this was amazing for me to see. People had written down theories of Dirac neutrinos before, but generally they involve, let's say, a fair amount of extra structure. Whereas here, this is just four-dimensional weakly coupled gauge theory. I haven't added any new fermions. Somehow the standard model fermions have it within their power themselves, essentially, to give you exponentially suppressed Dirac neutrino Yukawas. Okay. Now, let me move on to the quark sector. In the quark sector, we don't need exponentially small quark masses, but there is, in fact, a more subtle and more severe naturalness issue, which is known as the strong CP problem. In brief, the theory of quarks has a particular CP-violating parameter called the strong CP angle that combines the determinant of the up and down quark Yukawas with the topological angle of QCD, theta here, overall is called theta bar. And remarkably, from precision measurements of the neutron electric dipole moment, we know that this parameter in the standard model is less than 10 to the minus 10. Already that's amazing to learn, right? This angle could have been anything from minus pi to pi, and you go out and measure it, and it's less than 10 to the minus 10. But in fact, it's even worse, because for more than 2 generations, that is not the only CP-violating parameter that appears in the theory of quarks. For 3 generations, there's one more, which is this combination of the commutator of the up and down quark Yukawas, and this is something that we've measured, and it's order 1 in comparison. So this means that a small value of theta bar is not even technically natural. Theta bar is not the only parameter that breaks CP in the quark sector. And so this is a quite severe naturalness issue known as the strong CP problem, which people have been thinking about for a long time. Now, let me tell you about what was, in my mind, the most beautiful way this could have been solved in the standard model itself, a proposal from the 80s called the massless up-quark solution. For simplicity, let's just think about this in a toy model of QCD with only 1 generation of quarks. And the way this works is at some UV scale, you impose what's called a Peccei-Quinn symmetry. Peccei-Quinn means it has a mixed anomaly with QCD. It's anomalous. A Peccei-Quinn symmetry that just rotates the right-handed up quark. Now, when I write down the UV Lagrangian, I can only write down then the down quark Yukawa and some topological angle for QCD. In fact, this theory is CP conserving. We can make that more manifest by doing an anomalous field redefinition using the Peccei-Quinn symmetry of the up quark, which shifts, because it's anomalous, the theta angle, and just so manifestly makes the Lagrangian only the down quark Yukawa manifestly CP invariant. Great. So this is a theory in the UV, but of course we've known for many decades that the up quark has a mass in the infrared. That is in fact a feature of this. It's a Peccei-Quinn symmetry, so it gets violated by instantons. And as you flow down in energy, In fact, there are Tuft vertices of QCD that, just analogously to what we saw in the lepton sector, generate an up quark Yukawa from the down quark Yukawa. But because the UV theory is, we said, CP conserving, and instantons don't, inherently violate CP themselves, you generate an up quark mass now that is automatically CP conserving. So you get theta bar automatically equals 0 in the end. Now, of course, actually, in the standard model, we have 3 generations of quarks, so these Tuft vertices are much more complicated, and the most important instantons are at the QCD scale when the coupling runs strong, and we lose analytic control. So this was proposed in the early 80s, but the status of it was on ice for a few decades until fantastic efforts by lattice physicists unfortunately told us that the standard model does not bear out the massless up quark solution. The instantons of QCD are not powerful enough to account for all of the mass, all of the observed mass of the up quark. But now we have some generalized symmetry tool that can, from an infrared symmetry analysis, potentially tell us about new UV models where there can be additional instantons. So let's work analogously to in the lepton sector now in the quark sector and go and think about gauging flavor baryon number now. And it turns out in the quark sector, there is a slightly more subtle way you can do this because of the funny fact that we happen to have the same number of colors of QCD and generations of quarks. They're both 3. And that means now I can gauge a combination of flavored baryon number with some non-trivial global structure. So doing that, again, you have a U1 magnetic one-form symmetry. Actually, the important bit is a Z3 magnetic one-form symmetry, as you can see by, just like in the lepton sector, going through the non-abelian flavor theory of quarks, and there's a shared Z3 center that you can quotient out by, and you have this discrete magnetic one-form symmetry. And indeed, there's a non-invertible symmetry here. I'll say it on the next slide. It's a bit more subtle now. You have to understand the spectrum of fractional instantons. And okay, I'm skipping all of the technical details, which are in our paper if you'd like them. We'll talk about them later. But what you have to do a slightly more careful analysis of which symmetries are anomalous. Because if a global symmetry X, say, has an anomaly in an integer instanton background, then it's just fully broken. But if a global symmetry has an anomaly only in one of these fractional instanton backgrounds, which I'll remind you, you can't access on R4, then it becomes a non-invertible symmetry. And again, it turns out now in the quark sector, there is a non-invertible Z3 symmetry, which is just analogous to what we saw in the lepton sector. It gives left-handed quarks and up quarks the baryon number charge, but and generation independent, but gives down quarks the opposite charge. And so all of the down quark Yukawas break this non-invertible symmetry. And so again, following our strategy, we can look for a UV theory that introduces the appropriate discrete magnetic monopoles, and so generates this down quark Yukawa, all the down quark Yukawas. And again, once we know what we're looking for, it's not so hard to find. And this points to a beautiful theory of SU9 color flavor unification, which surprisingly has seen essentially no study before, but it turns out what you can do is put all 3 colors and generations of each quark into the fundamental of SU9 in this flavor unified theory, and then we can really just follow the same strategy we did before. In the UV now, I can impose a good Pechi-Quinn symmetry which acts on the down quarks, and so only write down the up-type Yukawa. I've put the top there because that's the largest. It's, again, generation symmetric. And I can write down the theta angle for this SU9 theory, of course. But again, it works just like the massless up quark solution. There's no strong CP violation to begin with. But then instantons, and now they look just like the one generation of QCD toy model before, instantons generate for us the bottom Yukawa. The down type Yukawas, the bottom Yukawa is the largest, but of course in a way that still preserves CP. And the instantons here are automatically more powerful because SU3 squared mod Z3 is non-trivially embedded in SU9 in a way such that as you go above the SU9 scale and you see the SU9 instantons, the coupling jumps up. So they're automatically more powerful, and you can generate the bottom Yukawa, all the down-type Yukawas from the up-type Yukawas. And so automatically get theta bar equals 0 into the infrared. Of course, there's tons of phenomenological stuff I'm skipping, but let me come to my conclusions, because it's 2024 and you have to back yourself. We've long understood that symmetries give us some crucial guidance to BSM physics. So, of course, we learn now that there's some broader class of symmetries that we ought to think about. That should give us lots of extra understanding into fundamental microphysics. As you can tell from my talk, so far my uses of generalized symmetries have really been quite basic. And yet, already we found new unified theories of the standard model fermions that have interesting instanton effects that can potentially solve standard model naturalist issues. So I think surely there is lots more for particle physicists to learn from generalized symmetries, and I look forward to it. Thank you.
So what's fractional instanton means?
An instanton solution with fractional instanton number. When you're on a manifold like S2 cross S2, something that has some 2 cycles, you can turn on magnetic fluxes around those cycles. And the instant
number, so you said it's a fractal Chern number?
I'll let a mathematician answer about the Chern number.
It's a PSUN bundle.
It's a PSUN bundle. That's what I was thinking.
It's follow-up on the same question.
Oh.
It's very strange that these quote-unquote fractional instantons generate local terms. Because if you take the gauge group and you replace the gauge group in your model by some multiple cover of it, these quote-unquote fractional instantons are not there, but all the local physics is unchanged.
Yeah.
So it's very strange.
So it's not the fractional instantons themselves, right? We're using an understanding of the fractional instantons as a tool to tell us about this UV theory where those are upgraded to integer instantons. Right? In the SU9 theory, they're just normal instantons, right? I could have, if I hadn't known about generalized symmetries, any particle physicist who didn't know about generalized symmetries could have, should have, in the past 40 years, just written down this SU9 theory from the get-go and said, these are just the instantons that told us about. I know it's an interesting theory from the UV. So indeed, the fractional instantons don't appear on R4, but we use them as a tool, a model building guide. Oh.
Thanks for the nice talk. So in the SU9 model, you again have a looks like a theta angle. So is that going to eventually be promoted to an axion, or what do you do with that? Or?
No, sorry, it's just like in the massless up quark solution itself. So there is this.
So theta 9 is not physical?
That's right.
Okay, I see.
Right, I mean, you could, if I do a rotation of the down type quarks here, then it's a Petit-Quint. They have a Petit-Quint symmetry, and so that would shift theta 9. And so I could do that good field reaction. Yeah.
Can I ask one more question? So did you also consider models with like one heavy generation relative with 2 lighter generations? Or so here it looks like everybody's on the same footing.
Indeed, everyone's on the same footing. I think that's a useful feature.
So top is way heavier.
Indeed. So of course, to get a realistic spectrum, you do need to have some. We also have all these extra gauge bosons, as was pointed out. You need to Higgs these, and the flavor structure has to come from Higgsing the flavor symmetry down into the UV, into the infrared. So indeed, I mean, at some intermediate stage, going from SU9 down to the standard model, you could try to break in a generation-dependent way. Absolutely.
Actually, a follow-up question related to Johnson's question. So this is a very nice way of generating this particular, or solving this particular problem, but how realistic can you make it, this SU9 model? Do you actually really need to separate out, have the Yukawa structure? This is a nice theoretical solution. If you actually want to do model building, you need to really get to the...
Of course, and so we showed in the paper, in principle, a way to actually generate the CKM structure. But there's, let's say, ongoing work on writing down a fully realistic model that actually does the flavor breaking, which, of course, as you said, is an important direction. Yeah.
One quick question is a comment on my previous questions. So when you gauge these U1 symmetries to make the neutrino mass natural, don't you also generate another naturalist problem for the mass of the Higgs that you introduce?
Well, unlike for the electroweak scale, supersymmetry could still be protecting the flavor scales of the universe. So, I mean, this is the problem with generally all unified theories.
So whenever you do this thing of gauging a U1, you have to imagine that there is some supersymmetry at a high scale that
it doesn't necessarily need to be supersymmetry, but indeed, you're right. I mean, you could think about further things. So you're right, absolutely.
Let's continue the discussion afterwards. Let's thank the speaker again.